In this video, we will continue our discussion of valence bond theory. This slide shows the various types of hybrid orbitals that are associated with the shapes from the VSEPR theory. So for example, if you have an SP hybrid, you would have two orbitals that form a linear geometric arrangement, and again the best example is beryllium difluoride. Whereas if you have a trigonal planar structure, this would require three orbitals to form the bonds, and this would be a sp2 type hybrid orbital. Note that the 2 is superscripted to the right of the p orbital, so there are three orbitals, three hybrid orbitals that result from the three atomic orbitals. And a tetrahedron requires four orbitals, and so in this particular case it would be an sp superscript 3, or referred to as sp3 type hybrid. Methane is a great example of that. In some cases where we can have exceptions to the octet rule, we would have a trigonal bipyramidal type structure where there would be 5 bonds. In this case, we have to start to use d orbitals. In this case, these are the d orbitals that are part of the inner shell, and so this trigonal bipyramidal structure is referred to as the sp3d hybrid combination, and PCl5 is a good example of that. And then finally, in an octahedral kind of shape, we need 6 orbitals. So we need 6 hybrid orbitals coming from an sp3d2 type hybrid orbital. So shown here are the two sp hybrid orbitals, focusing in primarily on the constructive interference, or the bigger lobes. So the lobe to the left would be one of the sp hybrids. The lobe to the right would be the second one. If we had an sp2 type hybrid, this points at the corners of a triangle, so these are all 3 sp hybrids superimposed on the same drawing. And then sp4 points at the corners, or excuse me, sp3 points at the corners of a tetrahedron, and then an sp3d type hybrid is for the trigonal bipyramidal structure, and then finally octahedral sp3d2. Just to remind you of how the hybrid orbitals are formed from the atomic orbitals of the atom. In this case, we are going to take a look at the sp3 hybridization. So in methane, so in this case, we would have a carbon atom that would have an electron configuration, a valence electron configuration of 2s2, 2p2. The energy diagram is shown here, where we have 2 electrons in the 2s orbital, and the final 2 electrons in the valence shell are unpaired and in the 2p orbital. In order to make 4 bonds, we need 4 unpaired electrons, so we're going to promote one of the 2s orbital electrons up into the empty orbital of the 2p, and this will then cause a slight stabilization of the p orbitals as they form the hybrids, and slight raising of the energy of the s orbital, so that we end up with 4 equivalent sp3 hybrid orbitals, each containing 1 electron. In this case, then, those electrons can then go forming bonds to other atoms and adopt the so-called tetrahedral shape. So this slide summarizes the process that one would go through to determine the hybridization of the orbitals necessary for a particular molecule. The first step is we would write out the Lewis dot structure for the particular molecule. We would then use VSEPR theory to determine the arrangement of the electron regions around the central atom. It is this electron arrangement that determines the hybridization. So we then have to take also into account the lone pairs of electrons. Step 3 from the geometric arrangement, we are going to determine that hybridization. And so we have to have the hybrid orbitals, the number of hybrid orbitals that corresponds to the number of bonds plus any lone pairs that are present. And then step 4, we would assign the valence electrons to these hybrid orbitals, and then final step, we would then use these hybrid orbitals to form these bonds. So as an example, we could take a look at sulfur tetrafluoride and describe the bonding and the type of hybrid orbitals necessary to form this molecule. The Lewis dot structure is shown here. You'll notice that there are 4 bonds between the sulfur and the fluorine, plus an additional lone pair. So in this case, this would adopt a seesaw type structure and would require 5 orbitals, which is based on the trigonal bipyramidal structure. The hybridization, therefore, is sp3d to account for the 5 hybrid orbitals that are required to make the bonds and the lone pair. To help you visualize how these hybrid orbitals are formed, we're going to look at an energy diagram again. So again, we'll look at SF4. In this particular case, the energy diagram has the valence orbitals where there are 2 electrons in the 3s, there are 4 electrons in the 3p, and the 3d shell is not occupied at all. In this particular case then, since we need to form 4 bonds plus a lone pair, we are going to need a slightly different arrangement of this, so we need to form our hybrid orbitals between the s, the p, and one of the d orbitals, atomic orbitals, and so therefore it results in this kind of energy diagram where the hybrid orbitals, there are 5 of them all at about the same energy, and the remaining 4 3d atomic orbitals are higher. We then will go ahead and put our electrons in. We're going to need to put in a total of 6 electrons into this. So we put the first one in, then the second, the third, the fourth, the fifth, following Hund's rules. The 6th electron will then be required to spin pair, and indeed that turns out to be the lone pair that is located on the central sulfur atom. And the remaining electrons then are paired up with the fluorine unpaired electrons, which then go to form our bonds. This slide gives you an idea of how the bonds might look when we have various kinds of overlap of orbitals that have electrons in them. So on the top here we have the bond that is formed between 2 hydrogen atoms. Since this is a direct overlap between 2 atomic orbitals, and we refer to this as a sigma type bond where the overlap is along the axis of the bond. Down below that is the overlap of the two p orbitals on two different fluorine atoms, which also points along the axis of the bond, and this is also referred to as a sigma bond, as you see in the lower right hand corner. In addition to the sigma type bonds that you can observe, when a molecule can have multiple bonds, either double or possibly triple bonds, it is also then possible to take the remaining atomic orbitals and have a sideways overlap of the atomic orbitals to form what are referred to as pi bonds. So as shown here, we have a sideways overlap of two p orbitals on two different carbon atoms, and this then results also in a constructive interference, but the overlap of these orbitals is not quite as good as what was observed in the sigma bonds, and so although these represent an attractive force, the force of attraction in a pi bond is not quite as strong as that in a sigma bond.